welcome to Deeptech Mash number 3. I hope you enjoyed 1 and 2. We haven't watched either of them, but we're told that some people have, which is nice.
Either that or we're just really wasting our time here.
It's warm, it's a nice place to sit, it's very comfortable. This one, we're going to focus on a particular topic rather than just riff all over the place, which has been our style so far, which may be why people liked it, but if so, this is a shame.
Click off now.
Click off?
Well, I mean, if they like
that,
yeah,
they should go. Yeah, you're right. So we're going to talk about photonics, and particularly sort of sparked by two things. One is Jensen Huang and his reveal of NVIDIA's sort of push into optical networking or optics to help speed up their compute. And second, Lawrence at Luna did a lovely blog on his Substack, which took apart some of the sort of elements of photonics, which we really enjoyed. And we thought we'd just chat around that area because we thought there was lots more to say. And Lawrence did an amazing job of teeing it up.
Agreed. I guess it's worth kind of painting the context more broadly. So, as everyone knows, AI models getting bigger and bigger are broadly, you train in a distributed sense. So across a number of different GPUs. It was a really awkward hat.
I don't know how to get to the water because of the microphone, but I'm sure there's a way. I'll figure it out while you carry on speaking. I'll figure that out.
And so you have to orchestrate training loads and inference across these GPUs. The GPU capacity is increasing, and essentially NVIDIA is saying that one of the bottlenecks will be at the networking layer. Photonics is a natural evolution of the kind of electronic domain that we exist in today. But it's a broad space and it touches on a number of different levels in the kind of hierarchy of the data center and the AI stack. So I think it's worth just kind of pulling it apart, exploring some of those areas and having a chat about what we think the potential is and where we think the risks and opportunities are.
Yeah. So sort of top level, so optical compute was kind of the starting point for at least what Lawrence was thinking about. And I think his conclusion, and I think we probably agree with this, is actual compute at the optical level is still kind of a long way off.
Mm-hmm. Yeah. I mean, I guess like in its extreme general purpose, compute in the optical domain is the furthest away, right? But even something, I think when you think about the challenges of optical compute, it's around there are two primary challenges around nonlinear kind of functions. Light tries to go in straight lines, and so you have to be a bit clever with how you actually can orchestrate signals to represent nonlinear activations. And then memory in an optical domain is also a pain. And the more that you have to convert from electronic to optical, the more expensive it gets.
I'd say, and it seems like the memory problem in particular is limited by the fact that you can do phase change memory, but the duration of those, or the amount of times you can cycle that memory before it sort of wears out is a problem. So optical compute has been an area that a bunch of startups sort of shot off into, and of all, it seems now sort of navigated away into a space that we're sort of calling optical interconnects in general. Do you want to kind of just explain what you think an optical interconnect is in that context?
Yeah. So I guess, going back to that kind of broader picture, if you think about where you're actually, say, doing kind of matrix math is in the processor, so in the GPU in the case of AI, and then you have to shuffle data across the network, right? And that can be between memory and processor, it can be between processors, it can be orchestrating the flow of requests into the data center. It's anything that is interconnecting a data source to the actual processor. And I think we've seen companies really attack that stack across the hierarchy. I think it's kind of useful to think about it in that hierarchical sense, from the lowest level being, can I essentially create like a short fat pipe that like means that I can get as much data as quickly as possible into a single processor.
So this might be like connecting up a few chiplets and some high bandwidth memory in one sort of small like compute cluster pod.
Yeah, or even in its like most basic, it's one memory to one, a memory system to a single GPU. And then I think you have and you focus on that high bandwidth memory to processor. And you then can think about things like little chiplets, like packages. So like you just described, you co-package a couple GPUs with some memory, and can you orchestrate the kind of network between it with optical setup?
And this is where a few of the kind of most well-known startups in the space have kind of pivoted from optical compute. So
Yeah,
Celestial, Light Matter,
IR Labs.
yeah.
Uh,
Yeah, although AR Labs maybe they started more focused on network. I don't think they were ever optical compute
Yeah,
themselves,
true.
but certainly Celestial and Light Matter, I think, have moved more into that domain.
Yeah, exactly. And I think, there's an argument to say that like they may still have on their roadmap, and their ambition is to scale that out and maybe eventually become fully
Yeah.
optical. It's a question of the feasibility of building in the short term, and also the kind of pull from the market. And right now, if you're NVIDIA is a scary kind of company to go up against on a purely inference side. So much of
Yeah.
our data center demand is being driven by AI, which has quite a specific workload as opposed to general purpose. And so, and there's this bottleneck occurring at the kind of networking level.
Is it worth like putting that then in context of what matters to the hyperscalers, the data center owners? Because this is a metric that I hadn't sort of thought about before, but it's bandwidth per like watt or unit of energy, which seems to be now the way that hyperscalers are thinking about sort of optimizing their data centers. It's like the metric that's most important to them. And that seems because actually data centers are power constrained,
Yeah.
i.e. like, the problem for a data center owner is not, specifically sort of how many GPUs they've got or how much latency is within the data center, but it's just how much power they can get into the data center is actually their biggest issue.
Yeah. And I mean, bandwidth per watt speaks on the networking side, and then you kind of have like operations per watt or some metric for the actual processing. And like at a collectively, that's the biggest cost and the biggest bottleneck for data centers is just being able to drive enough power into their data centers. I don't think, everyone has on their roadmap larger and larger clusters and bigger than it's that. There was a moment in time where I think DeepSeek kind of made people question that, but I think, it's kind of
that moment has passed.
Yeah. And we're back to the kind of hyperscale large compute clusters. So and in that situation, you inevitably run into some brick wall of how much power you can actually pump in. And so anything that optimizes the number of useful operations that you can get out for a given unit of energy. Yes, of course, it's great for the climate to reduce the amount of energy, but you can also drive renewable energy sources, right? And so you don't have to worry about that as directly. And from a data center perspective, I don't think, frankly, that's their biggest concern. It's more about how do I build the most competitive model in the world, and how do I service that best? So
those optical interconnect, that play of being able to move data more efficiently and therefore have your chip running more efficiently, is a big win. If you can get that to run in the data center context, I think I read that it was like 30 to 40% of the compute power was actually consumed by that sort of on-chip to memory like power data transmission problem. So that's a big gain, like a big gain for the data center owners if they can unlock much more compute per watt, I guess.
Yeah, I don't know. I see numbers ranging from like 20 to 40 or so. So it's somewhere that sits in the range there. But, I think it's undeniable that the biggest driver of energy and pull on energy is the actual processor. Yeah. But it's not insubstantial by any means, the kind of networking layer to it. But there's
I think it's that by making the connection to memory more efficient, you make the processor much more efficient. So that's where the gains are becoming with that optical interconnect.
Yeah, I mean, you can get better utilization. So I think it's interesting to think about, like, I guess when you start to daydream about like a fully optical, fully interconnected kind of system, what you actually get from that. And there are other companies that are working at, say, like the optical switching layer. So how do I actually, with the existing architecture of a data center, which typically is this kind of spine and leaf model of a couple hierarchies, where you end up with switches that manage the actual flow of information.
This is broadening out from quite short, fat optical pipes between clusters of chiplets or memory that you're sort of packaging together to how do you network out a full data center? Is that what you're describing?
Exactly.
There?
And so you could then take that approach and think, that we are going to provide and sell in the optical switches to enable an optical network,
Yeah.
or a more optical network. And that sits at that, and it's useful, and you can drive a lot of cost savings there as well if you can do the networking at a kind of optical level. But you still run into these bottlenecks related to the architecture. So if you, as I said, the data center typically follows this kind of spine and leaf model where you have hierarchies where information flows in and then is orchestrated back out of a centralized system. Optical networks can replace electronic switches, which it will save on a lot of costs, but you still end up with this kind of queuing, or the threat of queuing. So when you think about how networking can enable better performance, you think on it in two kind of primary ways, I think, which is latency reduction, like performance increases. So like it literally, if you can take out hierarchies in your switches, and you can move to fully optical, you're going to get faster communication between a given site. And if you can get rid of these hops of data, so going through nodes, you can get faster movement. And then on the other hand, you get better utilization. So, again, these kind of estimates vary a bit, but you get these reduce all kind of operations in large scale training where you're essentially bottlenecked by the slowest GPU, like cluster of GPUs. You send it back in to update the weights. And so if you can ensure that you're getting no queuing, super fast movement, and all-to-all connectivity, you get much closer to the theoretical optimal performance of a given GPU.
And this is why we're investors in Oriel, and this is kind of why we got excited about the Oriel kind of full stack, fully photonic, no electrical packet switching like solution they're developing, because it allows this solution that you're talking about.
Yeah, exactly. And I think we're slightly biased because we are Oriel investors, but like when you think about the kind of optical switching, that's a component that will sit in the stack of an Oriel and any other photonic network. The question is how you actually orchestrate a network of that scale, particularly as you start to think of an all-to-all thousands and thousands of GPUs connected across a data center. It's an ambitious goal, and one that George and the team have worked on for decades plus. Don't know how old he is. Maybe I'm aging him there, but and part of that is actually orchestrating all-to-all connectivity. Part of it is thinking about how you can actually basically optimize the network for kind of specific workloads. But it should also then enable you to kind of provide a solution rather than a component, and an end-to-end solution to end users. And it means that you can also save on CapEx costs around reducing the number of switches and reducing the kind of number of nodes that you need in order to orchestrate these networks. So you get savings across the board and performance increases if they can.
This is speaking back into this kind of bandwidth per watt like argument. I think Oriel are looking at kind of 3 orders of magnitude better in that space, so you could get massive performance improvements.
Yeah, you can get huge performance improvements, and you can also reduce, like I say, the kind of CapEx, OpEx. So, I think your biggest savings come from if you can architect your network to reduce the number of switches, as I say, and different things that you actually need to operate in because you're doing this new architectural approach. And then you get significant savings across training and inference from latency improvements, and you get significant improvements in utilization.
So if we're thinking about the landscape of kind of optical network compute at this point, you've got a bunch of players who are in the kind of interconnect space, and broadening out from there. So the very sort of, as you say, very simplistic, you've got a processor and you've got some memory and you've connected them with the fastest possible pipe. Then you've maybe got a few chiplets, and that's the kind of space that you see the products that the Celestial have and Light Matter and others on the market. And you've got people expanding out into network from there. You've got people trying to replace components of the network, so trying to put optical switches out there. And then you've got like Oriel who are trying to do a fully sort of photonic network. So you might have a light matter solution on chip, and then you might be passing that data out to an Oriel network to send around your data center. Is that how to be thinking about this space?
Yeah, potentially. And I would imagine Light Matter would say that their goal is to move into full networks. Right now, they're showing these slightly smaller clusters. the problem changes as you start to scale up to thousands and thousands of nodes, and you're operating more in the kind of what InfiniBand did for high performance compute, but for the AI world in photonics. And then you also have the kind of big NVIDIAs playing in the kind of co-packaged optics space, which actually does address a lot of it provides a lot of savings because they work in the photonics domain, and that's why they've been getting so excited about it. One of the challenges with co-packaged optics is that you essentially need to put more and more fiber optic cables. So you could think about it in like, if your road gets congested, you could either increase the number of lanes, or in an Oriole style approach, you increase the number of wavelengths. And so you save on the kind of capex, and a data center can then scale capacity without needing to lay more fibers. But I think co-packaged optics is an exciting kind of move in the industry that represents, I think, a real meaningful push in the direction of recognizing that actually photonics is here and now and necessary.
Yeah, if you think about the kind of hierarchy of when will various sort of future of compute innovations have a real impact on how we process data today, it certainly feels like optics is ahead in terms of moving data around, but not in terms of compute.
Yeah,
and even to the point where you look at something like quantum, which is making slow and steady progress towards to being useful. Optical actual fully compute almost feels behind that, and maybe longer term. But optics as a networking solution to move data around and allow the fastest processors today to operate as well as possible and not get limited by the amount of data they can get in and out. That seems like the biggest win in the near term.
Yeah, and I mean fiber optics transformed tons of our ways of transferring information, right? So like from that kind of side of things, I think we've recognized the power of photonics. It's actually orchestrating a system for an AI workload in a data center. And moving away from that kind of electronic packet switching, because I think we all recognize that if you could, you'd put a fiber optic cable down rather than a copper cable. But actually, how do you build this system? How do you create the switches? How do you actually enable light to stay within the optical domain across computations, or across orchestration in a network? I think the one maybe nearer term side, or that is slightly different, is kind of on the, say, free space optics for AI inference acceleration. That is, I think, slightly nearer
the side
term.
of thing like Lumia trying.
Yeah, exactly. They often use lenses to try and help them do this. You kind of trade off space essentially. You need a big box to do the performance. But because AI inference and an AI accelerator is essentially just repeated math, relatively basic math, like on scale, you can potentially build for that space slightly sooner. The hardest is like a general purpose processor of some kind.
What's kind of interesting to me about all of this is these are some relatively unsexy areas of compute that are suddenly becoming sexy. I don't think anyone was thinking about networking for a long time, particularly after sort of some big profile failures sort of 10, 15 years ago. Lawrence pointed out the problem with memory and how phase change memory is probably the place you'd go with for optical compute to be able to, but has had comparatively little investment. Memory's not been a place many people have invested, and so you're just starting to see these areas that are a bit sort of unloved, but suddenly real people or the investment community and the compute community thinking actually we need better infrastructure across the whole computational stack, and so we're starting to see some exciting moves in that area.
Yeah, for sure. I mean, I think optical memory, if you've cracked that code or anything like that, I think reach out to Dave and I first. But
anything in photonics, we're happy to have a chat.
Exactly.
It's a super interesting area for us.
But and I think there's a whole heap of areas that, like you said, haven't quite kind of hit the mainstream, but if we can find the kind of technical breakthrough for and the right team around, would be an amazing company to help support.
It's like a good example of this is like we know Walter at Fractal really well and what they're building, and we know that actually new forms of memory would add an extra order of magnitude onto the performance they're already able to deliver. And so you're just starting to see sort of all these different compute innovations suddenly going, we need better memory or we need better networking. So anything in that space, we're happy to look at, because we just think it's a super interesting area, because all the innovation is driving a load of other innovation. You're getting this kind of flywheel effect.
Yeah. And essentially, I think, we are in a compute paradigm shift, right? Like
Yeah.
where we are moving towards an AI first world where increasingly the majority of our kind of computational workload will exist within an AI framework. And so anything that enables that paradigm shift that allows like to kind of produce faster, better, cheaper, more intelligent models on scale is something that we'd love to chat about. I think it's also interesting your comment on unsexy areas becoming sexy. I think in general, generative AI has done that across the board. You know, like it's because it handles from a kind of algorithmic side, it handles unstructured data better than most or any previous kind of technology paradigm. It has meant that what was previously kind of siloed, walled, slow income like industries are getting a lot more attention, right? You think about kind of from construction to accounting agents to all sorts of different things that maybe weren't the sexy fintech and kind of opportunities from say like even 7 years ago. Have changed, and you go all the way down to the stack towards next gen memory to kind of processing chips. Like I think it's ushered in a kind of evolution in VC, which is reminiscent of where VC started in the first place. And I think that's a super exciting opportunity particularly when we think about the kind of wider geopolitical situation for Europe to kind of wrap their hands around it and actually build homegrown European giants and back their companies to go and do that.
Yeah, I mean, yes, we need a lot of capital here to do that. We need people with big pockets to take big risks, but we are starting to see a lot more of that. And so hopefully, the companies that we've mentioned, the UK, at least the UK or the European ones, like there is now enough capital around to support those and enough VCs willing to work together and collaborate to build like capital structures that help lift these companies into kind of, into being able to compete at a global scale.
Yeah, and then it's also buyers, right? Like the right ecosystem around the place to actually champion their own technology here and enable them to push forward. I think there is enough wealth in Europe. They just tend to want to spend it on, I don't know what Europeans spend their money on, yachts.
Yeah, maybe. I haven't got one yet though, so
well,
if a nice European would like to help me. But yeah, so that's it really. I mean, we've a bit of a dive through photonics. As we said, anyone out there who is building in the photonic regime or in any kind of compute area, next paradigm of compute, we'd love to chat. We think it's all really interesting. So come and reach out to us. That's probably it. We never know how to finish these. Yeah. So have you got any ideas?
No, but I was gonna end it on a next episode teaser. But the truth is that we don't know what our next episode is going to be exactly.
Put in the comments. Like I would like to say how much I dislike space tech.
Yeah, we were thinking about, and this is a dangerous game because when we say this and then no one writes anything in the comments, it's gonna be really embarrassing. Yeah. But like we were thinking about either defense tech / space, to make it even more juicy of a conversation. AI in the creative spaces, controversial, and AI for science. So whoever wants to see us and
like waffle on about those things.
Yeah. And hopefully in those situations, Dave and I may not agree. And then that's even more entertaining.
We don't agree on space tech as it stands. So
we do kind of. I'm just motivated to prove you wrong. But
that sounds like you don't agree.
Well, I'll save it for next time. But yeah, whatever anyone wants to listen to or any other suggestions, Dave and I will talk about.
Yeah, whack it in the comments or just any other abuse you'd like to throw at us. We happily take it.
Yeah. But yeah, I think that covers everything on Photonics. See you next time.
Lovely.
Goodbye.